So this is chapter 1, Physics and Measurements. And here we will see some basic things in physics, such as what is physics, some classification of physics, systems of units, unit conversions, something about dimensional analysis, and also significant figures. And then in the next chapter, we will start off with motion and other things. So first, what is physics? And we can say that physics is the study of matter and forces and energy and how they interact with each other, what are the effect of forces on matter, and so on. Physics is based on experiments, and after doing the experiments, we get some results, and those results are then cast into mathematical equations. Once we have a mathematical equation, we then have a definite result, a definite answer for some problem. And then we can use that to predict what would happen in other situations. Once these equations are verified, then they become physics theories and they become the laws. So there's a very close relationship between physics and mathematics. Of course, we also have descriptions of physical phenomena, but ultimately we want to place those descriptions in the form of mathematical equations. Physics covers the laws, physical laws, for everything from the tiniest particles to galaxies to the entire universe. And because it covers the fundamental behavior of matter as a result of forces and energies, so its laws applies to all the other sciences also. And that's why physics is called the queen of sciences. Now, physics has many branches, and we can classify physics in several ways, one of which is to classify it as either classical physics or as modern physics. So classical physics was what was developed before the year 1900 or around that time, and modern physics is after that time. So even modern physics is more than 100 years old. Now, classical physics itself has many branches, like classical mechanics. We deal with motion and forces, and the machines and the structures, the building that we have, follow the laws of classical mechanics, the effect of forces on objects. Thermodynamics is the study of heat and temperature, how things are affected by heat and temperature. And this is the basis. Thermodynamics is the basis for heat engines, like the automobile engine, power plants, and even refrigerators. Electromagnetism deals with electricity and magnetism, and it's the basis of electronics and electrical machinery and electric transmission. Vibrations and waves, sound and electromagnetic waves are covered here, and they deal with all aspects of sound and waves, waves in water, waves in air, even solids, earthquakes. Then we have optics, which deals with light and all phenomena related to light. Now, in modern physics, we have relativity, which is essentially mechanics or motion, but at very high speeds, and speeds which approach the speed of light, which we write as a c. This is the symbol for the speed of light. So when the speed of an object approaches the speed of light, some changes happen, and they are covered in relativity. In quantum mechanics, we deal with mechanics similar to classical mechanics, but here it's for very, very small particles, like molecules, atoms, and subatomic particles. And this mechanics is very different from classical mechanics. They behave very differently when we go on to that very tiny scale. Then we have astrophysics. We deal with stars and space and galaxies, everything to do with space. And particle and nuclear physics, we deal with atoms, nucleus, and the particles protons, electrons, and the subatomic particles, and even smaller than that, which we are not going to go into. And then there are many other fields. Now, in this course, in Physics 1, which is Physics 2325, we will be doing classical mechanics and thermodynamics. And in Physics 2, we will cover electromagnetism rather, vibrations and optics. And we will not cover these. There may be some minor reference to them as we go along. Now, if we look at the historical development of physics, so the Greeks made a lot of developments, but they were basically philosophers, and Aristotle made a lot of laws which were followed for about 2000 years, and even though they appear to be correct, but they were basically philosophers and not scientists. So they based things on assuming that the power of the mind is great enough that we can resolve every problem without doing an experiment. So for example, Aristotle said that a bigger object would fall faster than a smaller object, something that Galileo showed to be not true. But it appears to be like that. Big things seem to fall faster, but if we do an experiment, a careful experiment, we will find that that's not true. Also, Aristotle thought that if you roll an object and as it's with some initial speed, after some time it's going to slow down and stop. So the speed is going to become zero. So he proclaimed that the state of rest was the natural state of an object, and every state of motion will ultimately come to a state of rest. Philosophically, that may be okay. But we now know that it slows down only because there is a force of friction that slows it down. So if there were no friction, there would be nothing to slow it down, and it would keep on going. For example, the Earth has been spinning around its axis and going around the Sun for billions and billions of years, and apparently, though, slowing down is taking place. So they did make some rules and they did work for a while, but we find that experiments are essential. But there were some scientists in those days, like Archimedes, who did experiments on buoyancy and made the laws of buoyancy, which we still use. The ships floating in the water, in the oceans, are following those laws that Archimedes found, and water pump, and some other things that he made. And then we had some other scientists like Ptolemy. He predicted the positions of planets and eclipses and so on. And then around the 16th century, we had the age of experimentation. Galileo and others, they came around and they did experiments to verify all that they thought was true, and found some things to be not correct, and found other rules. Now, because we have experimentation, so we need instruments to do the experimentation. And if you have an instrument, you need a system of units. So if you're going to measure something then it's either going to be in meters or inches or feet or centimeters or whatever. So you need a system of units, which we will look into in the next video.